Hi, hello, I am Vidya Muradi from Bachelor in Medical Imaging Part-Time Cohort 4 from KPJ Healthcare University. Okay, my lecture in charge will be Madam Hardia, and today I'm going to present about subacute hazard static magnetic field. Okay, at first, let's start with the magnetic field. A magnetic field is an invisible area around a magnet or a current carrying wire that can attract or repel other magnets or magnetic materials. It's like an invisible force that affects objects with magnetic properties, pulling them closer or away. The strength of the magnetic field is usually stronger near the magnet or the current carrying wire and becomes weaker as you move away from it. Static magnetic field (MRI) is a widely used medical imaging technique that relies on strong static magnetic fields with radio frequency fields and pulsed magnetic gradients to create detailed images of the body's internal structures. While MRI is generally considered safe, just because it's not using any radiation, but still there is a hazard behind it. While MRI is generally considered safe, it is essential to understand and address potential subacute hazards associated with static magnetic field. A static magnetic field is a field that has a constant strength and direction over time. It does not exhibit any variation or fluctuation. The strength of the static magnetic field is measured in Tesla, which the International System of Units, that means SI unit for magnetic flux density. Smaller units such as Gauss are also sometimes used where 1 Tesla is equal to 10,000 Gauss. In the context of MRI, the static magnetic field used is typically quite strong. Common field strengths, like most of the hospitals, they are using 1.5 Tesla, and sometimes some of the hospitals they are extend to the 3 Tesla. Research and specialized imaging may involve even higher field strengths. Subacute hazard. In the context of MRI, safety subacute hazard typically refers to potential risk or adverse effect that may arise from exposure to the magnetic fields and radio frequency energy used in the MRI process over a relatively longer period but still within a defined time frame. MRI is considered a safe diagnostics imaging technique when proper safety guidelines and protocols are followed. However, there are certain safety considerations, and exposure to the strong magnetic fields and RF energy can have both acute and subacute effects on individuals. First, MRI biological effect. What is biological effects? In MRI is considered safe technology since it can change the position of atoms but not alter their structure, composition, and properties as the ionization radiation attempts to do. However, as in any sanitary intervention, there are intrinsic hazards that must be understood, acknowledged, and taken into consideration. These hazards are relative to all three types of fields which can affect patients, staff, and other persons within the MR environment. Biological effect. Tissue heating. Static magnetic fields such as those generated by magnetic resonance MRI machines or other strong magnets have the potential to induce tissue heating through several mechanisms. When the human body is exposed to a strong static magnetic field, it can lead to the following effects. Second, eddy current. Static magnetic field can induce electric currents in tissues known as eddy current. These currents circulate within the body and the resistance of tissue to the flow of these currents leads to the generation of heat. Dielectric heating. The interaction of the static magnetic field with the body's tissue can cause dielectric heating. This occurs due to the rotation of water molecules and other polar molecules in response to the magnetic field leading to the generation. At first, let me explain about the tissue heating. Potential risks associated with prolonged exposure to static magnetic field. At first, Thermal tissue damage. Thermal tissue damage, prolonged exposure to strong static magnetic fields, particularly in conjunction with radio frequency pulses in MRI, can result in excessive tissue heating. This heating may cause thermal damage, as I mentioned earlier, to sensitive tissues, particularly in areas where efficient heat dissipation is challenging. Second, cognitive effects. Cognitive effects. Some studies have suggested potential cognitive effect associated with prolonged exposure to static magnetic fields. While the mechanisms are not fully understood, there are concerns about possible impacts on brain function. Next, implant interactions. Implant interaction. Individuals with metallic implants or devices may be at risk of experiencing heating or other adverse effects due to interactions between the static magnetic field and the metal. The movement induced in metallic objects within the body can lead to heating and potentially cause injury. It's important to note that the risks depend on the strength and duration of exposure as well as individual health factors. Next, biological effect. Peripheral nerve stimulation. Peripheral nerve stimulation occurs when time varying magnetic fields induce electric currents in peripheral nerves, leading to the perception of sensation or muscle contractions. This phenomenon is more relevant in the context of rapidly changing magnetic field, such as those used in transcranial magnetic stimulations (TMS) or certain type of medical devices. These are the potential risks associated with the peripheral nerve stimulation. At first, discomfort and pain. Peripheral nerve stimulation can cause discomfort or pain depending on the strength and frequency of the induced currents. Unintended stimulation of nerves can lead to sensations ranging from tingling to painful muscle contractions. Second, muscle contractions and spasms. In certain causes, peripheral nerve stimulation can result in involuntary muscle contractions or spasm. This can be particularly problematic if it occurs in a critical area or during activities that require precise motor control. Next, limitation in device use. Peripheral nerve stimulation limits the usability of devices in certain applications. For example, in TMS, the strength and frequency of the magnetic field need to be carefully controlled to avoid unwanted side effects. Overall, understanding and mitigating these risks involve careful consideration of magnetic field parameters, appropriate safety guidelines, and continuous monitoring during the use of devices or procedure involving static or time-varying magnetic fields. Implanted device and foreign bodies. Implanted device and foreign bodies can interact with static magnetic field, particularly in environments such as magnetic resonance imaging facilities. The interaction between magnetic fields and metallic implants poses potential risks, including displacement, heating, or malfunction of the implanted device. First, displacement of implants. Metallic implants may experience forces and torques in the presence of a strong static magnetic field. Second, heating effect. Metallic implants can absorb radio frequency energy during an MRI scan, leading to heating. This is more common with implants that have a significant length or are composed of materials with high magnetic susceptibilities. Third, malfunction of implants. Some implanted devices, such as pacemakers or neurostimulators, may have electronic components that can be affected by strong magnetic fields. The magnetic field can interfere with the proper functioning of these devices, potentially leading to malfunction or failure. Let's go to the safety guidelines. Patient screening and education. Develop a comprehensive pre screening questionnaire to identify metallic implants, devices, or objects. Provide clear instruction on removing metallic items such as jewelry, watches, and clothing with metal components. Ensure the availability and proper use of metal detectors during patient screening. Establish a process for addressing identified metallic objects, including the possibility of rescheduling or using alternative imaging methods. Secondly, educating patients about risk and safety measures. Develop educational materials such as like brochures, videos, or presentation slides explaining MRI safety guidelines. Conduct pre-procedure counseling concessions to address patient consent and ensure understanding. Ensure the regular refresher courses personnel keep personnel updated on the latest safety guidelines and technology advancement. Personnel training. Importance of well-trained MRI personnel. Establish a comprehensive training program for MRI personnel covering safety protocols, emergency procedures, and effective communication with patients. Okay. Implement a mentorship system where experienced personnel guide new staff in MRI safety practices. Minimize the risk of errors or oversights that could compromise patient safety. Handling emergency situations and ensuring patient safety. Develop and regularly review emergency response plans for scenarios such as allergies reactions, equipment malfunction, or patient distress during the MRI. Conduct regular drills to stimulate emergency situations and assess personnel readiness. Establish communication protocols to ensure quick response coordination among MRI staff, emergency responders, and other relevant healthcare professionals. These are the references that I have been used in these slides. Okay, thank you so much for watching. Bye.